Thank you, Mr. President, for giving me the floor. Before starting, I would like to thank the members of the jury of their presence today, as well as my thesis supervisor, Professor Zugar and Professor Krajic, for their guidance and support throughout the thesis. The thesis that I am submitting today for discussion by the jury is entitled Transition Toward 100% Renewable Energy System by 2050. In order to present our work, this presentation is subdivided to 5 parts. First, we will start with an introduction, then we will present the forecasting of energy demand in different sectors. After that, we will discuss the municipal solid waste management, later the 100% renewable energy systems. Finally, we will present our conclusions and perspectives. Let us begin with introducing the general context, the problematic, and the objectives of this thesis. The first thing that came in mind in this context is why we need to maximize the penetration of renewable energy in the energy mix. Well, in addition to climatic impact, Morocco is heavily dependent on fossil fuel. Such dependence will grow in proportion to the demand growth. Hence, the need of the maximal use of the renewable energy potential. The literature of the renewable energy transition have shown that there is a huge gap between the interest shown by the developed countries and the developing countries regarding the feasibility studies of the 100% renewable energy system transition. Such gap is really pronounced in MENA region, hence in Morocco, this study aims to fulfill this gap. Currently, Morocco's objectives are only specified in terms of installed electric power while relieving non-electric energy demand. In 2018, the share of installed renewable energy is 38%. In the future, Morocco intends to increase its installed capacity to reach 80% by 2050. Unfortunately, we have not found any detailed study of future final energy consumption. Consequently, these objectives remain vague, lacking precise roadmaps. In order to understand these issues, we need first to try to answer these two main questions. What would be the energy demand in 2050? How to succeed the transition to a 100% renewable energy system by 2050? For the first problematic, we must examine all the data we have at our disposal. The IEA provides a history of total energy demand as well as the energy demand by sector from 1990 to 2017. These are the most disaggregated level we have so far until now. The question that arises now, can we predict the demand from each of these sectors from historical data? In other words, is this data alone are enough to forecast future demand? The answer of this question is quite complex. The prediction is the image of the type of the data that we have. Highly aggregated indicators such as total final consumption and less aggregated indicators such as energy intensity sectors can be found in the IEA database. On other hand, more aggregated indicators are unavailable for Morocco and for developing countries in general. I would like to remind you that the quality and accuracy of the prediction takes into account the quantity and quality of data available. Can we therefore develop specific models for each sector in order to generate these missing data? The second problem is to try to answer the question how to succeed in the transition to a 100% renewable energy system by 2050. We must know if this transition is realistic from a technical point of view, can it be allowed from an economic point of view, and can it be achievable while respecting the political constraints? In summary, the objectives are designing the appropriate mathematical approaches to analyze energy consumption in different sectors using the socio-economic parameters of Morocco, and also to predict the national need for renewable energy supply for 100% renewable energy system supply for different scenarios. Moving now to the energy demand approaches for each sector. Starting first with the transport sector. The transport sector is made up of four main modes of transport, and each mode of transport is made up of one or more types of vehicles. These vehicles can be classified into two categories, one for the transport of passengers in gray, and the other for the transport of freight in orange. Each vehicle can have one or more types of fuel. This introduction of the transport system is necessary to know the future trend. In fact, to predict future consumption, we must first try to determine the main factors that describe the history of consumption. According to the literature, the most detailed equation of this purpose evokes a number of energy indicators that are not available so far. So that the total energy is the sum of the energy demand of all types of vehicles. The equation involves three different indicators for each type of vehicle: vehicle stock, average distance, and specific consumption. Unfortunately, these indicators are not available in Morocco. However, most of the developed countries collect these indicators. To sum up, currently we have only the total energy as data. However, the energy efficiency indicators in Morocco are unavailable. This prevents an accurate and rational prediction of energy demand. To fill this gap, we used neural networks to generate the missing data that best describes the energy demand curve. To do this, we have collected these indicators from 28 European countries, and we tried to, to find a correlation with the socioeconomic data of each country using neural network. The richness of the database allows for a good learning. The indicators generated by these models are used to calculate the total energy using the equation described previously. The calculated energy is then compared to the real total energy demand for each country and for each mode of transport. The results are presented for 28 European countries for the road mode. It compares the energy demand from the generated data, which is marked in blue, with the actual energy in red. The R square is calculated to perceive the prediction quality of the model. All R squares are superior than 95, higher than 95%, which clearly indicates that model is quite accurate. The same quality of indicator generation is seen for the rail, air, and water. Now that the model has been available, has been validated, and the learning phase is over, the socioeconomic data of Morocco are introduced into the model in order to generate the missing indicators. The generated indicators are used to calculate the total energy using the same equation used previously. The calculated energy is then compared to the real energy demand. As a result, we can see that the curve calculated based on the indicators and the real curve are strongly correlated with an R square of 95.7%. This error is the cumulative error during the generation of the indicators. Nevertheless, the error is tolerable, which demonstrates the effectiveness of the method in generating consistent energy indicators. Moreover, these indicators can now be used to describe the entire future transport system in Morocco. If we want to predict future energy demand, we just have to integrate the future socioeconomic indicator until 2050. It is now possible to evaluate the variation of the future energy demand under different scenarios. First scenario consists of predicting energy demand without integration of energy efficiency measures. Second scenario consists of reducing of fuel economy potential according to the European legislation. A third scenario assesses the gradual introduction of electric cars. The fourth scenario evaluates the redistribution of the production of the distance generated by the passengers PKM and the distance generated by the freight TKM. The strong point of these two indicators is that they make it possible to identify the distribution of the most used vehicles for people and goods. They involve two important parameters, which are the average occupancy and the average load. The result of these calculations shows that the most used vehicle by Moroccan passengers are cars and trucks for transporting the freight. The question that now arises is what will happen if we can change this distribution from an energetic point of view. In this sense, for the same total PKM generated from each year, the fourth scenario increases the PKM by increasing the average occupancy, increases buses PKM by increasing the average occupancy, and decreases the number of vehicles, the number of cars. Regarding the freight transport in this sense, the fourth scenario assumes the increase the TKM of the trains by increasing the average load, reduce the TKM of trucks by reducing the number of trucks, and reducing the TKM of light vehicles by reducing the stock of light vehicles. In addition, scenario 4 evaluates the replacing of diesel with potential biofuel from the biodigestion of municipal waste on the impact of CO2 emission. In terms of energy savings and CO2 emissions, the results show that scenario 4 is much better than the other scenarios. In addition, by introducing biofuel, CO2 emissions can be further reduced. Turning now to the potential of the industrial sector. The industrial sector is composed of 7 different sub-sectors. We remind here that we want to predict the future energy demand while we only have the total energy of the total industrial sector. The particularity of the sector is that it is highly dependent on import and export. Therefore, it was necessary to consider the quantity consumed and not the quantity produced to describe the energy curve. Knowing that we have the quantity of goods consumed, the idea here was to construct an equation that links the energy consumed to the energy demand, using the energy intensity factor for each industrial subsector. With this equation, we can identify the impact of efficiency measures on the future demand. If we now want to predict the future energy demand, it is enough to predict the quantity of consumed quantity. To do this, we have tried to describe this consumed quantity QC by different economic indicators using multiple linear regression. Comparing the consumed quantity generated by the model with actual data, the results show a strong correlation for all subsectors except for textile with a relatively lower R square. The irregularity is accentuated in 2011. This is probably due to the free market agreement with Turkey for textile imports. By calculating the energy from the previous equation, the results presented here represent a comparison between the calculated energy demand and the real demand. With an R square greater than 95%, the two curves show a good correlation. Furthermore, I would like to draw your attention to the right-hand curve. Before the development of the model, we did not have the energy demand by each sector. But thanks to this model, we have an idea about the energy demand for each sub-sector. By introducing now the future socioeconomic parameters of Morocco until 2050, we could obtain the future energy demand thanks to the energy efficiency measures. By reducing the energy intensity factors, Morocco can reduce its industrial consumption up to 1 megaton in 2050. With reduced consumption, these results show the consumption by energy type for the entire industry sector. Turning now to the prediction of the building energy demand. Remember that the objective here is to predict the future energy demand as accurately as possible. According to the literature, the equation that best describes the energy demand of buildings is given by the equation presented here. It invokes several parameters. The only data that we could be collected are the total energy demand and the building area. However, data on the other six parameters are not available in Morocco. For the detailed descriptions of the energy demand, we divided the buildings into 8 buildings types and their characteristics. In addition, we were able to collect the building components of the actual buildings without insulation, of course. To summarize, we have data on the surface area of the buildings, the total energy demand, and the building materials. On the other hand, we do not have the energy demand of for each type of building, the projection of surfaces, and the energy efficiency indicators. To generate these missing data, we thought of combining the two bottom-up and top-down approaches in order to propose the optimal efficiency measures later. To take into account the detailed characteristic for each building type, we use the Revit software, which is based on the BIM language. This tool allows to integrate a very detailed level of design. We have therefore built the 8 types of buildings: flat, villa, typical house, commercial building, administrative building, school and university, hotel, and hospital. We have considered all components of the building envelope for exterior walls, for interior walls, roofs, and glazings. Let's start with the determination of the thermal demand for the buildings built so far. To do this, it was necessary to identify the climatic variation in terms of heating degree days and cooling degree days. The results are shown in these two figures. In order to have single map that takes into account both conditions, we thought of summing the values of both maps for each point. In the new map obtained, we have subdivided the climatic zones into 6 zones. Then we have distributed the buildings on the different climatic zones. In fact, we will simulate the thermal demand by implementing the 8 types of buildings in each climatic zone. The thermal demand results are therefore given for each type of building and each type of each climatic zone. Then we looked for the optimal values in terms of lighting power density, electric equipment power density, lighting schedule, and power schedule that would allow us to have an energy demand closest to the real total demand. In the same way, it was being identified the cooking power density, number of hours of cooking per day, water heating power density, number of hours of water heating per day. To validate these parameters, we calculated the total electrical demand and the gas demand and compared them to actual demands. With an R square greater than 94% of for both demands, we can conclude that the curves are well correlated. Having identified the different parameters of the equation, oh, let's now proceed to the projection of the energy demand. Let's start with the projection of the building surfaces, building area. Using multiple linear regression, we were able to describe the evolution of the area as a function of macroeconomic indicators. Now let's proceed to the projection of the fraction F of building equipped with HVAC. Based on the IEA study, we were able to obtain the fraction of 5 different years as we needed the fractions for each future year. We proposed a polynomial fraction of degree 3 that links the 5 points. Now we will proceed to the prediction of the thermal demand. I remind you that we have already defined the thermal demand for each type building and for each climatic zone, assuming that there are no thermal insulation measures. The question here is, can we propose optimal efficiency measures in the future? To answer this question, we use the tool called life cycle cost. These indicators allow us to calculate the construction cost of a building as well as the energy cost necessary to satisfy the energy demand. If we plot the ratio of alternative options and the reference as a function of energy savings, we generally obtain a curve of this form. The optimal solution is the one that represents the lowest LCC ratio. To do this, we tested all possible options in terms of energy efficiency measurements using this algorithm. It is an iteration algorithm that uses nested loops to get all the values of the LCC ratio and their associated energy savings. The efficiency measures we have tested are specific to the glazings, window stores, degree of orientation, wall construction, roof construction, HVAC efficiency, lighting efficiency, and infiltration. Reference is in red and alternative options are in black. The results obtained are different for each type of building and for each climatic zone. For zone 1, for example, 8 curves are presented here. Each curve corresponds to a building type. The optimal solution corresponds to the minimal LCC ratio. The same goes for zone 2, zone 3, zone 4, zone 5, and zone 6. Now the question is how to interpret these results. To answer this question, we went back to the algorithm and identified all the measures that allowed us to obtain this minimum. For the flats, for example, different measures are recommended for each climatic zone. The same goes for the villas, typical houses, commercial buildings, administrative buildings, schools and universities, hotels, and hospitals. Once we have identified the optimal energy efficiency measures as well as all the parameters of the equation, we can calculate the total energy without energy efficiency measures, a second scenario that involves the efficiency measures, and a third scenario that identified the impact of switching from LPG to electricity in case LPG is no longer subsidized by the state. So the results for scenario 1 are presented in this figure. The demand amounts to almost 140 terawatt. While in the second scenario, the total energy demand is only 103 terawatt. In order to make the implementation of the recommendation realistic, we propose here a progressive integration of over 10 years between 2020 and 2030 using an S-curve. The results of the third scenario, which evaluates the substitution of LPG by electricity, show that energy can be reduced by 10% in 2050 compared to the second scenario. This reduction is due to the fact that the electric cooking and water heating equipments are more efficient than those that use LPG. This scenario is interesting from the point of view that LPG that will no longer be subsidized by the state. After a 10-year economic study, the use of electricity will be more profitable. Citizens will naturally turn to electricity. We will now proceed to the valorization of municipal waste from an energetic point of view. The High Commission of Planning has made a projection of the generation of municipal waste until 2050. It also provides the comparison of its waste. Most of it is attributed to municipal waste, to organic waste. According to the Environmental Protection Agency, each waste management practice has an energy cost for each material. A positive value indicates that indicates an energy expenditure. A negative value indicates an energy gain. The same goes for CO2 emissions. A positive value indicates CO2 emissions and negative value indicates the amount of CO2 avoided. Based on these two tables, several scenarios can be evaluated. The first scenario, which will be used as a reference, evaluates the current practices. The second scenario proposed to replace open-air landfills by incinerations, as well as CH4 recovery after landfilling. The third scenario evaluates the increase of the recycling rates. The last scenario introduces composting. Currently, Morocco recycles only 6.3% of its waste. 30% of the rest is buried in the ground without energy recovery, and 70% is sent to open-air landfills. In the second scenario, it is proposed to recover the methane from the landfill waste and incinerate the parts sent to the open-air landfill. The scenario increases recycling to a maximum of 22.4%. The fourth scenario, it is proposed to compost the organic materials for agriculture purposes. The results are presented in terms of energy savings and CO2 avoided. Scenario 1, 2, and 3, scenario 3, 2, 3, and 4 are all compared to the baseline scenario. They all show negative values, which means that all alternative scenarios are better than scenario 1. The most interesting scenario from an energy and CO2 emissions point of view is scenario 4. Now, proceeding to the economic and technical evaluation of 100% renewable systems. After answering to what would be the energy demand in 2050, summing the energy demand of all sectors without energy efficiency, the total demand can be as high as 357 terawatt-hour. On the other hand, this demand can be reduced by 40% by adopting the optimal energy efficiency measures just defined. After defining the energy demand in 2050, I remind here that the second objective of this research is to find an optimal solution to meet this demand under the constraints of 100% renewable energy supply. We will first identify the constraints related to the supply of demand not affected by the reduction of energy efficiency measures in accordance with the vision of Morocco to 2050. The second scenario evaluates the supply of demand that is curtailed by energy efficiency measures, which we call EEM. The last scenario evaluates the transformation of the whole system into renewable energy and not only the electric part. Let's recall here that the objectives in Morocco is to reach 80% in insulated power to cover the demand in electricity. On the other hand, the transition to non-electric part is not possible for the moment. The demand in this scenario is a demand that is not subjected to energy efficiency measures. The second scenario is a bit more ambitious. For a reduced demand by the optimal energy efficiency measures, we expect to cover all the efficiency demands in 2050 by different renewable plants. In order to reach 100% renewable energy system, we also need to cover the fossil energy demand with renewable energy. Regarding this limitation, the third scenario evaluates the possibility of replacing this part of fossil energy with methane via the digestion of municipal waste. On the other hand, methane production is limited by the amount of municipal waste generated each year. For example, in 2050, we expect to produce 11 terawatt-hour of methane, which is not enough to cover all the fossil fuel demand. For this, we have thought of producing hydrogen gradually to meet all the fossil demand in 2050. On the other hand, the production of hydrogen, which is done by the electrolysis of water, will certainly increase the electricity demand. To increase grid flexibility and reduce the need for storage due to its high cost, we have proposed to integrate vehicle to grid (V2G). V2J. For this, we considered a car park composed of five most common types of cars with their own storage capacity. The energy is calculated from this equation, take into account the sharing and discharging efficiency. Charging and discharging efficiency. It is also assumed that the car park at the parking cars connected to the grid will gradually increase. We also thought of reducing the electricity demand by introducing desalination plants. In fact, the specific consumption of desalination plants consumes less energy than conventional water treatment plants. Electricity demand is calculated by the following equation. The results that we present here represent the total energy demand for each scenario and for each year in terms of electricity, fossil fuel, biomass, and CH4. The demand for renewable electricity is given by respecting the hypothesis that we presented earlier. The question now is how to meet the demand for renewable the demand for renewable electricity. For scenario 1, Morocco's vision favors wind power for electricity production. By calculating the LCOO, we notice that it is quite high. Can we reduce the LCOE? Is this the optimal distribution? For the second scenario, we thought of looking for the optimal fractions for each type of renewable power plant. We used this cascade algorithm to test all possible fractions to have the minimum LCOE. It was found that LCOE can markedly decrease by promoting CSP. The same algorithm is used for the third scenario. Now that we have the demand, supply, storage, and different costs, we have used the energy plan software, which is the most suitable tool for the dimensioning of large scales. In order to determine the total cost of the system, the capacity of the cables and for import and export, vehicle-to-grid connection capacity, desalination plant capacity, electrolyzer capacity, and GHG emissions, under the constraints of critical excess of electricity production. The results shown here represent the primary energy supply for the three scenarios for all the Moroccan energy systems for the different years on the left axis, as well as the CO2 emissions on the right axis. We note that the alternative scenario is more energy intensive than the second scenario. This is mainly due to the high electrical demand for the production of hydrogen. From an economic point of view, the alternative scenario is clearly the most advantageous since it is completely independent from the import of fossil fuel energy. Since the third scenario is the most advantageous, we present here the minimum capacities to be installed each year in terms of vehicle-to-grid, electrolyzer, and desalination plants. We can also have an idea of the minimum interconnection capacities that must be installed with neighboring countries. To conclude, we have generate models that generates missing data. We have modeled. We have also forecast energy demand by 2050. We have also made it possible scenarios for reducing consumption in each sector. We have also given the different scenarios of energy transition towards 100% renewable energy system. For the first scenario, by maintaining Morocco's current strategy, and a second scenario by increasing electricity production to 100% renewable, and for the third scenario by introducing vehicle-to-grid desalination H2 and CH4. For the outlooks and perspectives, we can give this the question of what can we have beyond the 100% renewable energy systems. We can look for increase the feasibility of increase in electricity production in renewable energy to promote exports, can identify renewable energy sources to be promoted. We can also make the study of the reliability of the electricity network, and also we can conduct a technical study of the electricity network under the constraint of the massive integration of vehicle to grid, desalination, and H2. We have conducted several scientific publications in highly impact factor journals, and we have also uh, participate in international conferences. Thank you very much for your attention.